Good day to all of you. In today's lecture, we will go through the basic converter circuit topologies and identify a different mode of operation which is common among all kinds of switched mode power converters. So, what you see here in this slide are the three basic canonical form converters. The first converter, which is the buck converter, what you see here, right, which steps down the DC voltage from a source voltage of Vg to an output voltage of V naught, which is less than the source voltage. Then we also looked at the second converter, which is the boost converter. This is a canonical model where the source voltage Vg that you see here is boosted up to a voltage of V naught, which is higher than the input voltage. And the third canonical circuit, which is called the flyback converter or the buck boost converter, where the source voltage Vg is converted to V naught, and V naught can be anywhere between anywhere below Vg or above Vg. Now, in all these converters, if you notice the circuit diagram, the freewheeling path is through a diode. The freewheeling path in each one of them is through a diode, right, in this. And on account of this, when we have a current flowing through the inductor L, what you see here, when you see a current flowing through this inductor L I naught, this can flow only in one direction because the diode in all these circuits are present in that part of the circuit, and it will not allow the current to change direction. So, the SPDT, single pole double throw switch, that we use in all these canonical circuits consists of an active switch, which is the transistor, and a passive switch, which is the diode. And in this kind of realization, they do not allow the current in the inductor to be bidirectional. It supports only unidirectional current. So, on account of this, the inductor current cannot change direction, and this gives rise to two different operating modes in these converters, and these operating modes are the continuous current mode of operation and the discontinuous current mode of operation. Now, in this lecture today, we will try to go through what is the special features of these two operating modes, and how does one get the converter gain in operating mode 1 or in the continuous current mode of operation or in the discontinuous current mode of operation. So, we will take first the buck converter, and then the boost converter, and then the flyback converter, and go through the process of the freewheeling duration and try to see if the current does not change direction and what are the consequences of that depending on the different operating conditions in the converter. For example, the inductor current in these converters is positive, and it has two regions, one rising region of current di by dt greater than 0, and another falling region where di by dt is less than 0. Under steady state of operation, the current is periodic. So, the fall in current in the off period and the rise in current in the on period are equal, and we get an inductor current which is positive all the time and continuous. So, let us look at what happens to this inductor current on certain changes in the operating condition. We can consider the condition where we have the inductance value being reduced. For example, the inductor L is reduced from the previous value of L1 to L2 and L2 is less than L1, the consequence of this is that the current in the inductor is now swinging between larger values of delta I. This is a consequence of lower value of inductance. In a similar way, it is possible to look at the inductor current when the switching period is changed or switching frequency is changed. For example, if the switching frequency is changed from TS1 to TS2, so you can see that now the rising region of the inductor current is prevailing for a larger duration and the falling region of the current is also prevailing over a larger duration. On account of that, this swing delta I or the ripple current has increased compared to the previous condition. If the switching frequency is decreased, current ripple increases. In the earlier case, we had seen that if the inductance value reduces, the ripple current is increasing. In the same way, we can also look at the change in the load current. If the load current changes, the net average current in the inductor has dropped down, but the ripple current remains the same. Or if you see the ripple factor, which is delta I expressed over the average current, that increases. So, we find that there are three possible directions in which the ripple current is affected, and these three can be summarized as change in L. If inductance becomes smaller, the ripple current increases. If the inductance is higher, ripple current will decrease. Then change in switching frequency or switching period. If the switching frequency drops, ripple current increases. And the third one is the load. If the load current is reducing, then also the ripple factor or the ripple current is increasing. So, these are the three parameters which are governing the ripple current or the ripple factor. Now, the consequence of these changes can be seen in a particular mode of operation. For example, if the inductor current increases in the on duration of the switch to some value, and during the off duration of the switch, when the inductor current is decreasing, supposing if the inductor current comes to 0 even before the end of the cycle ends at this point Ts, even before the end of the cycle, if the inductor current comes to 0, then we see that the current cannot reverse in direction on account of the diode in the circuit. So, during the short interval between the time the diode current comes to 0 and the time when the next cycle starts, the diode and the transistor both are off. So, we say that there is a third state when the diode, transistor, both of them are off. So, we have an interval T1 when transistor is on, we have an interval T2 when diode is on, and we have an interval T3 when TR, transistor and diode both are off. So, now unlike the previous mode of operation where current in the inductor was continuous, where we had only two intervals, sub intervals in one cycle, the sub intervals where transistor is on and diode is on, and the next cycle starts. Now, in this mode of operation, there is a third interval when both the transistor and the diode are off. Now, this particular mode of operation is called discontinuous conduction mode of operation, DCM mode of operation, and you can see that it has an interval T1 when switch is on. okay, which is what is shown here as the first interval, where the current is increasing. Then we have an interval T2 when the diode is on. So, during this interval, whatever stored energy in the inductor is lost and eventually it comes back to 0 before the end of the cycle. If the cycle ends at Ts, even before the end of the cycle, the energy in the inductor is completely lost and the diode in the circuit ensures that the current cannot reverse in the inductor. So, that being the case, we have a third interval, which is when both the transistor and the diode, are off and the inductor is now just floating. No current is flowing through the inductor and the inductor is floating. On one end is V naught, the other end is not connected anywhere and the current through the inductor is 0. This is the third interval, the T1 interval, T2 interval and T3 interval. T1 is when the switch is on, T2 is when the diode is on and T3 is when none of them are on, all of them are off. So, in one interval, one in switching period Ts, there are 3 sub intervals T1, T2, T3. T1 is the interval which is the duty ratio of the switch called D. T2 is the interval, we might call this as the diode conduction ratio, which is D2, and the rest of them is 1 minus D minus D2. So, that all of them together add up a total switching period, normalized switching period of 1. So, we have a duty cycle D, a diode conduction ratio D2 and then the rest of the cycle time 1 minus D minus D2 and the total switching time, which is normalized to be 1. Now, in this particular slide, you see that these 3 intervals in one cycle Ts, there is an interval T1 when the diode is transistor is on, then there is the next interval T2 when the diode is on, then the last interval T3 when none of them are on and so the current through this is 0. This third interval is 0. Now, the conversion ratio can be found out just as we did for the other converters by taking the VL, the inductor voltage in one cycle and finding out the volt second balance on that. This volt second balance, as we see over one period, now consists of the interval T1 when the voltage is Vg minus V naught and interval T2 when the voltage is minus V naught and the interval T3 when the voltage across the inductor is 0 or the inductor is just floating. So, if we now write down the volt second balance equation for the inductor, it consists of totally 2 sections. During T1, a voltage of Vg minus V naught is applied across the inductor. During T2, a voltage of minus V naught is applied across the inductor. So, we define this ratio T1 by Ts as the duty ratio D, T2 by Ts as the duty ratio D2. This is the duty ratio of diode conduction time. This is the duty ratio of switch conduction time. And if we write the volt second balance in terms of voltage multiplied by time, it can be expressed in terms of these ratios as D times Vg, the main switch duty ratio times Vg is now D plus D2 times V naught. Okay, this equation, if it is written in terms of duty ratio, you can divide everywhere by Ts and write it in this form. And from this it is possible to find out the voltage conversion ratio and it is D by D plus D2. Now, in continuous conduction mode, you will find D2 will be the entire 1 minus D and the denominator will become 1 and conversion ratio is just D. In the discontinuous conduction mode, there is a duration in every cycle when the inductor is left open. On account of that, the duty ratio M is now d divided by d plus d2, what we see here. Now, this d and d2 are related to each other. Normally, when we operate the converter, we control only d. d2 is based on the stored energy in the inductor at the start of the freewheeling interval. During the first interval T1, the inductor charges up starting from 0 current. It charges up to a current of IP. Depending on what is this peak current, in the next interval T2, the inductor loses all its energy. So, there is a certain rate of rise of current in this interval, which is decided by the voltage across the inductor during on period. There is certain other di by dt during this diode conduction interval, which is decided by the voltage across the inductor during the diode conduction period, and there is a time when the voltage is 0 across the inductor or the inductor is left floating. So, it is possible to resolve this d2 as a function of d by realizing that the net DC current flowing out of the inductor is the output load current. The inductor current is shown here in this red waveform. The average value of that is same as the output current, and if we relate this, it is possible for us to find out what is d2 in terms of d. For example, the peak current is decided by the off interval d2 Ts multiplied by the di by dt during the off interval, that is d2 Ts into V0 by L. This tells us what is the peak current reached in the first interval. Then during the second interval d2, this energy is completely lost, and we can say that the average value of the waveform that we saw in the previous one, average value of this is IP by 2 on its own base, and because this total duration is, total ratio is d plus d2, the average current is 1/2 IP into d plus d2. This is the average current, which is V0 by R. I0 is same as V0 by R, and this IP we can replace from the first equation. So, that now we get a result that V0 by R is same as 1/2 of d plus d2, d2 Ts V0 by L, and here V0 is on both sides. If we cancel that, this is simplified into a relationship. V0 is cancelled, and this 2L by RTS can be taken to the other side. So, you see a relationship d2 into d plus d2 is k. This can be written as a second order equation in d2, namely d2 square plus d2 minus k equal to 0. So, for the buck converter, the relationship between d and d2 is related through this quadratic equation in d2. So, from this equation it is possible to evaluate d2 in terms of d. Naturally, it will also be a function of k, and this k is defined as the conduction parameter. It is related to 2L, it is related to L, it is related to R, and it is related to Ts. We had seen graphically right in the beginning that the conduction, whether it is continuous or discontinuous, has three significant causes. One of them is the value of inductance, the other is the frequency, and the third is the load. We saw three different causes which can force the inductor current to come closer to 0 and get into discontinuous mode of operation, and we see that this effect is consolidated by a single parameter called k, and this k is 2L divided by RTS. Now, this quadratic equation can be solved so that we can write d2 in terms of d and k. So, this is the relationship between d and d2, and if we now substitute back in the first equation, it is possible to find out the conversion gain m as a function of d, which is duty ratio, and conduction parameter k. which is this 2L by RTS. Okay. And this is also the same as d by d plus d2. So, V naught by Vg can be expressed in terms of d and d2, or V naught by Vg can be expressed in terms of d and k, or alternately you can express it in terms of k and d2 also, in terms of any two of the other variables. Now, we see that in comparison with the continuous mode of operation, this function is from d, it has become d by d plus d2. And in the discontinuous mode of operation, d plus d2 is always less than 1, because the total switching period Ts has T1 plus T2 plus T3, and d plus d2 is a ratio of only 2 of the intervals. The third interval is not counted. So, we see that this addition d plus d2 will always be less than 1. So, the conversion gain d by d plus d2 will be always greater than d, which is the continuous mode operations conversion gain. So, we can say that the conversion factor in discontinuous mode of operation is always more compared to the conversion factor in the continuous mode of operation. Okay. Now, we can also find out when does the converter operate on the border, that is, we can say that it is both in continuous mode of operation or in discontinuous mode of operation. For this to be true, it is very easy to see that the current has to start from 0, go to a peak, and when exactly the cycle ends, it has to come back to 0. So, that T3 is 0 or D2 is 1 minus D. We can also say that when D2 is 1 minus D, just equal to 1 minus D, the operation will be on the border, and when D2 as calculated from this is greater than 1 minus D, converter will be in continuous conduction, and when D2 calculated as per this relationship, if it is less than 1 minus D, the converter will be in discontinuous mode of operation. So, if you substitute that particular relationship, we find that if this 2L by RTS, which is called the conduction parameter, if this is equal to 1 minus D, the converter will be in the operating in the continuous mode. If it is more than 1 minus D, it will be in the continuous mode of operation. It will be less than 1 minus D, it will be in the discontinuous. When 2L by RTS is greater than 1 minus D, operating mode is in continuous mode of operation. When 2L by RTS is less than 1 minus D, operating mode will be in discontinuous mode of operation, and when 2L by RTS is equal to 1 minus D, the operation will be on the border between continuous and discontinuous operation. Now, we can define this function 1 minus D as a critical value of k, and if k is greater than that critical value, operation is in CCM, and if k is less than that critical value, operation is in DCM. This is the border. It can also be seen in a graphical form. We can plot the critical value of k, conduction parameter, as a function of D. This is duty ratio. K critical is 1 minus D, and it will be a function starting from 1 ending up 0, because when D equal to 0, K critical is 1, and when D equal to 1, K critical is 0. And the conduction parameter of the converter is 2L by RTS, that will be a fixed number for a converter. So, when you compare both of them, you can see that at some point they both may be equal, and on the left hand side of that, the blue region is where this K critical, which is 1 minus D, that is more than 2L by RTS, or 2L by RTS is less than K critical, operation is in discontinuous mode of operation. On the right hand side, 2L by RTS is more than 1 minus D, so operation is in continuous mode of operation. So, graphically it is possible for one to find out what is the region in which the conduction will be in continuous or discontinuous mode. There is an important observation here, the critical conduction parameter is 1 at the most, at all other points it is less than 1. Supposing if this 2L by RTS is let us say greater than 1, is equal to let us say 1.5. Such a converter will have this L always above 1, and so it will never be operating in discontinuous mode of operation. Such a buck converter where the inductance, resistance and switching time are such that this quantity is more than 1, such a converter will never operate in discontinuous mode of operation. Only if this is less than 1, following this picture, it is possible to find out what is a region when conduction is discontinuous and what is a region when conduction is continuous. We had seen that in the discontinuous mode of operation, the gain is always more than the gain for continuous mode of operation. So, from this picture you can see that this is the duration of D where K is greater than K or K is less than 1 minus D. So, that blue region is when the operation is in discontinuous mode of operation. This is the blue region. So, in this region the function D, which is our gain in continuous mode of operation, is shown by the dotted lines here. But because it is operating in discontinuous mode of operation, the gain is more than what we would have got by this bottom line. So, in the blue region the converter produces a voltage which is higher than what it would produce in continuous, but after you have moved to the yellow region, the gain is given by D, which is the duty ratio. So, it is possible to see graphically how the conversion, the operating condition will be in DCM or CCM, and if it is in DCM, how the gain will be more than the normal continuous conduction gain and so on. Now, the important features, the salient features of discontinuous mode of conduction are summarized here. You can see that every cycle the current in the inductor starts from 0. So, because it starts from 0 current, the turn on loss in the transistor or in the switch is 0. This is a very important advantage, because now it is possible to switch the converter at higher and higher frequencies, because the switch on loss, the switching on loss has come to 0. And during the off period, the diode recovers smoothly with a finite di by dt. So, at the end of this diode conduction period, the recovery current through the diode is limited and the recovery charge is also limited, and the diode recovers very softly. This is a second advantage. This has a significant influence on the EMI generated by the converter, the electromagnetic interference, because at all the instances you find that the current in the conductor has a very defined, well defined d by dt. There are no sharp rise in current, and if there are no sharp rise in current, there will be no sharp rise in magnetic field around the inductors, and so the EMI effect will be very good. This will not have too high frequency or very high frequency electromagnetic interference effects. Another significant feature is that because the ripple current is large, we can manage with low inductance in the circuit. The filter inductance L is now smaller compared to continuous current mode, and if the inductor is smaller, the size of the inductor also will be small, the weight of the inductor will be small, and the weight of the overall converter can also be small, and it is possible to achieve a higher power from a lower weight of the converter. And because of these advantages, there are some situations where the discontinuous mode of conduction is preferred. The disadvantage is that the inductor ripple is large, and so the inductor has to be designed for a higher value of peak current. Right? So, this is a compromise which one has to accept. There are several advantages. At low power levels, these advantages are significant compared to the disadvantage of high inductor current ripple, and so there are many converters which are consciously selected to operate in DCM operation if the power level is low. These are the salient features. Now, we will go on to see the same effect of the operating modes of discontinuous mode of conduction and the continuous mode of conduction on the second converter, which is the boost converter. What you see is the boost converter, which converts the source voltage Vg to a load voltage V naught through an inductor L, an active switch transistor T or S, and a passive switch, which is a diode. The features are very similar. If we draw the inductor current in any one of these converters, when you are operating in discontinuous mode of conduction, it is very easy to identify the operating mode if we look at the inductor current. Inductor current will have now the 3 sub intervals in one circuit. If you call 0 to Ts as the full circuit, you have now 3 sub intervals T1, T2 and T3. And this T1, T2, T3 are just as we had seen before. T1 is when the active switch transistor is conducting, T2 is when the passive switch diode is conducting. So, if you call this as T1 for the active switch and T2 for the diode, and T3 is when none of them are conducting. And the conversion factor is obtained just as before, finding out the volt second balance in the inductor. What is the voltage and duration during the on time? What is the voltage and duration during the off time on the inductor? It is possible to write down simple volt second balance on the inductor as you see here. We define the active switch duty ratio as D, the passive switch duty ratio as D2, and write the volt second balance as Vg. When the switch S is on, the voltage across the inductor is Vg into T1. When the switch is off, voltage across the inductor is Vg minus V naught into T2, and during the third interval the inductor is floating. So, if we add up these volt seconds, what you get is Vg into T1 plus Vg minus V naught into T2, and this total has to add up to 0 for steady state, and this can be written in terms of duty ratios as D plus D2 times Vg is D2 times V naught, and this results in the conversion ratio, which is D plus D2, the ratio of the active switch on time, passive switch on time divided by the passive switch on time, D plus D2 divided by D2. In the continuous conduction mode, D2 is same as 1 minus D. So, the numerator becomes 1 and the denominator becomes 1 minus D. The difference compared to the continuous mode of conduction is that you have now in the numerator instead of 1 D plus D2 and in the denominator instead of 1 minus D, D2. So, this voltage conversion ratio also requires resolution of D2 and D. As before, it is possible to evaluate D2 in terms of D by finding out what is the average current flowing out of this. Average current flowing out of this is the whatever hashed area I am showing here. If that is averaged over one cycle, that will give the average current, which is I naught, and that is shown as I naught is average over D2, because D2 only the current is going to the output, and this can be written in terms of this peak current. The peak current is the slope during the Vg into D times Ts is T1 and Vg by L is the slope during the on time. So, the peak current is given by this expression, and if we express the average current in terms of all these quantities, you get now the relationship between D, D2 and K as before, where K is the same conduction parameter for all these converters. It is the ratio of 2L by RTS, and the interesting point is that this conduction parameter has no dimensions. It is a dimensionless parameter, so that whatever units you use is 2L by RTS. If you use consistent units, K will always be the same number irrespective of what units are used. So long as consistent units are used, the K will be a parameter which has no dimensions, and so it is constant irrespective of the units that are used. And this second order quadratic equation, which relates d d2 square minus k d2 minus k d equal to 0. So, this is the quadratic equation relating d and d2, and it is quite easy to find out what is d2 in terms of d and k. So, this is that relationship. We can resolve d2 as a function of the conduction parameter k, a function of conduction parameter k, and the switch on time d, a function of k and d. And as I said before, it is also possible to write d as a function of k and d2 or k as a function of d and d2 through all these relationships. And we can substitute now that value of d2 back in the original conversion gain equation to find out what is the conversion gain V naught by Vg in terms of d and k. So, now V naught and Vg is not just a function of d. In continuous conduction mode, V naught by Vg is just 1 by 1 minus d. It is a function of only one variable d, whereas now it is a function of the load also, d and k, not load, k, conduction parameter, which is a function of L, Ts and R. Just as before, this conduction discontinuous mode of conduction results in a gain. During that time, the ratio of V naught by Vg or the conversion factor in the discontinuous mode of conduction is always more than the conversion factor in the continuous mode of operation, and these things can also be seen in the form of our graphical form. We can find out the value of k for which this d2 is 1 minus d in this relationship. If we put that in here, k critical is that value of k when d2 is 1 minus d, or that value of k when the converter is operating on the border between DCM and CCM. In this particular converter, boost converter, this critical value of k is d into 1 minus d whole square, and it is possible to, once this k critical is defined, we can find out when the converter will be in CCM operation and when will be in DCM operation. This can be seen in the form of a graph, a graphical form. So, as d varies from 0 to 1, this k critical is now starting from 0, reaches a peak and comes back to 0. In the buck converter, we saw that this function was 1 minus d. So, it started from 1 and came all the way to 0. Now, it starts from 0, k critical is d into 1 minus d whole square. So, when d is 0, k critical is 0, and when d is 1 also k critical is 0, both values, and this k critical has some maximum at some particular point in between, and you can see that that maximum occurs when d is 1 by 3 and this maximum value of k critical is 4 by 27. Okay. And it is very easy to see if the value 2L by RTS, if k is greater than k critical, the converter will be in CCM, and if this k is greater than k critical, again it is in DCM, and in between region where k is less than k critical, this is a region where k is less than k critical, the converter is operating in discontinuous current mode of operation. Again, you can see that because this k critical has a maximum value of 4 by 27, in boost converter, if 2L by RTS, if this quantity 2L by RTS is greater than 4 by 27, the converter will never go into discontinuous mode of operation. It will always be in continuous mode of operation. And it is also possible to relate in the discontinuous mode of operation what happens to the conversion gain. What you see here is the function conversion gain as a function of D if the converter is operating in continuous mode of operation. We know that in the discontinuous mode of operation, the gain is more than the continuous mode gain. So, actual gain follows this curve, maximum of the two things, and in this DCM mode of operation, the gain is more than the continuous mode of operation. So, what we had seen in the boost converter also has the same features, that the turn on loss is 0, inductor value is low, the recovery of the diode is soft, and then the ripple current is large. These are the salient features of the converter. What we see here is the third canonical form or the third basic converter, which is the flyback converter. Now, flyback converter takes in the energy during the on time from the source and supplies the energy during the off time to the load. You can see that the polarity of power is also changed, polarity of voltage is also changed. Sometimes this flyback converter is also called inverting buck boost converter. That is, the output voltage can be in magnitude less or more than the input, buck or boost, but the output polarity is opposite to that of the input polarity. So, flyback converter, non-isolated flyback converter is also called in some literature as the inverting buck boost converter, which is what is shown here. Output polarity is of this polarity and input polarity is plus and minus. Now, the continuous current mode and discontinuous current mode are characterized by 3 intervals. Very clearly it can be seen on the inductor current waveform, the interval T1, and the interval T2, and the interval T3. T3 is when none of the devices are conducting, inverter is floating, and there is no energy drawn from the source, no energy supplied to the load side from the inductor. The conversion gain for these converters follows the same procedure that we find out under steady state what is the volt second balance on the inductor. For that, find out what is the voltage across the inductor during the switch on time, which is Vg in this particular case. During the on times, this is Vg, and during the off time, this is V naught. So, you can find out the volt second balance, finding out Vg into T1 plus V naught into T2. Third interval does not contribute to the volt second, and if you add all these, Vg into T1 plus V naught into T2, that adds up to 0, and that gives us the relationship in terms of the duty ratios. D times Vg is minus D2 times V naught, or V naught by Vg is the ratio of D by D2 with an inverting sign for the change in polarity. It is a ratio of the duty ratio of the switch divided by the duty ratio of the diode, D by D2. In a conventional continuous current mode of operation, this D2 will be equal to 1 minus D, and this relationship we had seen earlier, that ideally for the flyback converter, the conversion ratio is minus D divided by 1 minus D. Now, instead of the 1 minus D in the denominator, the inductor de-energizing or inductor discharge time is now not 1 minus D, it is only D2, and on account of that the ratio is just minus D by D2. This voltage conversion ratio will be higher than what we had seen in continuous current mode as minus D by 1 minus D, because D2 is less than 1 minus D. As before, D2 and D have to be resolved if we want to get output voltage purely as a function of the duty ratio and the parameters of the converter. We follow the same principle, that we find out what is this load current which is supplied here, I naught. I naught is the same as the average of the inductor current during the diode conduction time. Diode conduction time is D2, conduction time ratio is D2. So, 1 by 2 IP into D2 will be the average current of what is shown in the hatched region, and that is the same as I naught. So, as before, we can write I naught as half of I p into d2, the way I had shown the hatched region, and I p itself is the on duration d and Ts multiplied by the slope in the on time, which is V g by L. So, now if this I p is replaced in this, you get I naught is V naught by R, which is the same as 1 by 2 d2 dTs V g by L. And if you bring this V naught here, and this V naught by V g can be replaced by d2 by d, this d will cancel, and you will find that 2L by RTS, which is k, is nothing but d2 square. So, if this is simplified, it turns out to be k is equal to d2 square. If I simplify all those things, and k is our same conduction parameter, a dimensionless parameter decided by the inductance in the circuit, resistance of the load, and the switching period Ts. All these quantities d and d2 are related through the parameter k, and you can simply now in this converter write d2 as square root of k. Right? It is not even related to d, it is simply a function of k only in this particular converter. So, we can say that d2 square is k, or d2 is root of k, and V naught by V g we had seen is d by d2, which turns out to be d by root k, square root of k. And d2 being less than 1 minus d, the conversion factor in discontinuous mode will always be more than the conversion factor in the continuous mode of operation. In this mode, this conversion factor will be more. The critical conduction parameter is found out by finding out what is d2 in the border of discontinuous conduction and continuous conduction. On the border, d2 is same as 1 minus d. So, if we substitute this in this relationship, the critical value of k is that value of k for which the converter is on the border between continuous and discontinuous mode of operation. So, that value is characterized by this relationship, that 2L by RTS is equal to 1 minus d whole square. If 2L by RTS is more than this quantity, the converter will be in continuous mode of operation. If 2L by RTS is less than this critical value, the converter will be in discontinuous mode of operation. So, we have seen this, we define this, we define the critical value of conduction as 1 minus d whole square, that is the border value, and if k is greater than that border value, you are in continuous conduction, and if k is less than that border value, the operation is in discontinuous mode of operation. Again, this also can be plotted in the form of a graph, so that it is very easy to look in one place in a picture what will be the operating mode, what is the gain, and so on. We have seen for this flyback converter, the critical value of k is given by 1 minus d whole square. So, we can plot that, write that as a function of d. When duty ratio varies from 0 to 1, now this critical value follows a second order curve 1 minus d whole square, and finally, when d is 1, critical value is 0, when d is 0, critical value is 1. In the case of buck converter, we saw that critical value of k was just 1 minus d, so it followed a straight line connecting 1 at this end and 0 at this end. But in the flyback converter, this critical value is a second order relationship, k critical is 1 minus d whole square. So, this is a parabola. For example, if duty ratio is 0.5, at that time k critical will be 0.25. And then you can also on the same graph, you can put the conduction parameter k equal to 2L by RTS. So, if this line is drawn on the same picture, then you can see that where this meets the critical value of K, that is the point of duty ratio where the conduction is on the border between discontinuous and continuous mode of conduction. On the left hand side, this blue region is where L is less than K critical, conduction parameter is less than K critical. If that is so, the converter is in discontinuous mode of operation. On the right hand side, this is K and this is K critical, K is greater than K critical, and on the yellow region or on the right hand side region, the operation is in continuous mode of conduction. Just as we had seen in the other converters, in the buck converter we saw that the maximum value of K critical is 1. In the boost converter, the maximum value of K critical was 4/27, and in the flyback converter, the maximum value of K critical is 1. That occurs when duty ratio is 0. So, if we select our converter design such that 2L/RTS is greater than 1. For example, any converter, if we select a switching frequency high enough, so that Ts is small enough, this K can be made greater than 1 and the converter will always be in continuous mode of conduction. So, even for a converter which is designed with certain value of L and for certain load condition, it is possible to take it from discontinuous mode of conduction to continuous mode of conduction just by changing the switching frequency, following this relationship, that if 2L/RTS is greater than 1 minus d whole square, then the converter will come into continuous mode of operation. So, many times if we prefer continuous mode of operation in a particular converter, we can always change the switching frequency, so that the converter can be brought into continuous mode of operation. Now, in the continuous mode of operation, in the region where the operation is discontinuous and the region where the operation is continuous, this is the gain with continuous mode of operation. In the discontinuous mode of operation, the gain definitely is going to be something more than this. It is because in the denominator now we have d/d2. Earlier it was just d/1 minus d. Now, the denominator, this m in continuous mode of conduction is d/1 minus d. This m in discontinuous mode of conduction is d/d2, and d2 is always less than 1 minus d if you are in discontinuous mode of conduction. So, from this you can see that the gain in the continuous mode will be more than the gain in the discontinuous mode, and you can see that in the discontinuous mode the actual gain will be more than what you get in the continuous mode, and on the border they both of them are equal, they follow the same curve as before. So, it is this type of graphical representation can give us instantly, if you overlay on this what is the value of K and what is the value of K critical, you can instantly find out the region of discontinuous mode, the region of continuous mode, and then the additional gain which is d/d2 in the discontinuous mode of operation. All this can be plotted nicely on a graph and understood fully. Okay. Now, again finally to summarize, what we notice is that the discontinuous current mode of operation has 3 intervals in one cycle, T1, T2, T3, and recognizing that a converter is in continuous mode of operation or discontinuous mode of operation is quite simple. All that one has to do is to monitor the current in the inductor. If the current in the inductor has 3 distinct sub intervals, switch on time, diode on time, and then diode switch, both of them are off, T1, T2, T3, then you can conclude that the converter is operating in discontinuous mode of operation. Or if you do not measure it, if you know the conduction parameter, if it is less than K critical, then also one can say that it is in discontinuous mode of operation. This K critical is 1 minus d in the case of buck converter, d into 1 minus d whole square in the case of boost converter and 1 minus d whole square in the case of flyback converter. So, if we find out what is this conduction parameter 2L by RTS in any converter and try to compare it with the K critical, it is possible to find out whether it is in DCM or CCM. If you have access to the current in the inductor, it is directly possible to find out the intervals and do that. Now, there are many positive advantages of discontinuous mode of operation. The first advantage is that because the current starts from 0, the converter turn on loss is practically 0. So, the switching loss, half the switching loss is eliminated. It is possible to switch at higher switching frequency. Because the switching loss is now low, you can go to higher switching frequency, and because the switching frequency is higher, the inductor value, capacitor value and so on will reduce. The second advantage is that the diode recovery process is very soft. The current in the diode smoothly comes to 0 and stays at 0 with smooth recovery of the diode. This is very good from EMI, electromagnetic interference, created by the converter on the surrounding environment. So, this is a very good advantage, especially if you are switching at high switching frequencies. We also get an advantage because we have to use a small value of inductance. The current ripple being high, inductance value is smaller. So, it will be size will be smaller, cost will be smaller and so on. The disadvantage is that the inductor current ripple is high, but if this compromise can be accepted, mostly it is acceptable in low power converters where the currents are not very large. Many designers consciously choose discontinuous mode of operation if the power levels are small, 10 watts, 20 watts, 30 watts, 50 watts. At smaller power levels, discontinuous mode of conduction can give you advantages in efficiency, in EMI performance and in overall cost and size. What we have seen up to now, we have summarized as two different modes of operation in all these converters are possible, because the freewheeling diode or the diode conduction period cannot support current in both directions, and these two different modes of operation are named as discontinuous conduction mode and continuous conduction mode. And it is possible to find out the border between the two modes of operation by looking at the conduction parameter of the converter K, which is the ratio 2L by RTS, which is a dimensionless parameter, and compare it with a critical value of K, which is a function of the duty ratio for different converters. For buck converter is 1 minus D, for boost converter it is D into 1 minus D whole square and so on. So, by comparing the conduction parameter, it is possible to find out the operation, or you can consciously choose the conduction parameter by a high switching frequency. So, that the converter will operate in discontinuous mode of operation and gain all these advantages. So, with this we will stop on the different modes of operation. In the following lectures, we will spend some time on solving a few problems related to the steady state operation of different types of power converters, both in continuous mode and in discontinuous mode, different circuit topologies, different power conversion levels and so on. Thank you very much.